Everything you know will end. Not tomorrow, not in a billion years, but eventually, inevitably, the universe itself will die. For decades, we thought we knew how. A slow, cold death, the big freeze, an eternal darkness where even atoms themselves drift apart in an infinite void. But what if we were wrong? What if the universe isn't destined to freeze at all, but to collapse back into itself in a catastrophic implosion? New data from the most ambitious cosmic survey ever conducted suggests our universe's death sentence may have just been rewritten, and the implications are staggering. In the high desert of Arizona, atop Kitt Peak, sits an instrument that's changing everything we thought we knew about reality. The Dark Energy Spectroscopic Instrument. DESI. Its mission? To map the universe in 3 dimensions, not hundreds of galaxies, not thousands, millions, 6 million galaxies across 11 billion years of cosmic history. Each one a data point. Each one a piece of evidence in the largest cosmic investigation ever undertaken. Night after night, DESI turns its gaze to the heavens, capturing the light that has traveled across unimaginable distances and unfathomable spans of time. Light that left distant galaxies when our solar system was still forming. Light that carries encoded within it the history of cosmic expansion. And what it found defies explanation. For the past century, we've watched the universe expand. After the Big Bang, galaxies rushed away from each other, spreading out like fragments from an explosion. That much we expected. That much made sense. But in 1998, 2 teams of astronomers discovered something that shouldn't be possible. The expansion wasn't slowing down. It was speeding up. Galaxies weren't just drifting apart. They were accelerating away from each other, driven by a mysterious force we call dark energy. A force that makes up nearly 70% of everything that exists. Those astronomers won the Nobel Prize. Their discovery became the foundation of modern cosmology. We built an entire model of the universe around one fundamental assumption. Dark energy is constant, unchanging, eternal. A cosmic force that permeates every cubic centimeter of space, pushing everything apart with relentless, unwavering strength. According to this model, the universe would expand forever, accelerating into infinity, until every star burns out and even black holes evaporate into nothing. The Big Freeze. The heat death of the universe. An end so distant and so cold that even time itself becomes meaningless. Our inevitable end. Except DESI's data suggests that assumption might be catastrophically wrong. To understand what's happening, we need to talk about lambda, the cosmological constant. Einstein introduced it over a century ago, then called it his greatest blunder. But after 1998, lambda became cosmology's cornerstone. It represented dark energy as a fixed property of space itself, unchanging across all of time. If lambda is constant, the math is simple. The universe expands forever. Galaxies drift beyond our observable horizon. Stars exhaust their fuel. The cosmos grows dark and cold. Eventually, even matter itself decays. The Big Freeze. It's a bleak ending, but at least it's predictable. At least we understood it. But DESI has mapped the expansion history of the universe with unprecedented precision, and the pattern doesn't match. Not quite. The data shows something unsettling. Dark energy appears to be weakening, not dramatically, not suddenly, but consistently, measurably, over billions of years. The force that's been pushing galaxies apart may be running out of steam. Think about that for a moment. If dark energy weakens, the expansion slows. And if it weakens enough, if it continues this trajectory, the expansion could stop altogether. And then what? Then gravity takes over. Every galaxy, every star, Every particle in the universe begins falling back toward everything else. The expansion reverses. Space itself contracts. The Big Crunch. Not an infinite cold void, but a violent, apocalyptic compression. Galaxies collide. Stars merge. Space-time itself collapses back into a single, infinitely dense point. The universe doesn't freeze. It burns. DESI's findings didn't come from theory or speculation. They came from raw observation, from measuring the precise positions and distances of millions of galaxies across cosmic history, from analyzing light that has traveled for billions of years to reach us. The instrument uses something called baryon acoustic oscillations. Think of them as cosmic fossils. Ripples frozen in the distribution of galaxies, echoes from the universe's first moments after the Big Bang. When the cosmos was just 380,000 years old, sound waves rippled through the hot plasma of the early universe. These waves left an imprint, a signature scale in how matter clustered together. By measuring these ripples at different distances, at different epochs in cosmic history, DESI created a map of how fast the universe was expanding at each point in time, a cosmic timeline stretching back billions of years. And that map reveals a pattern. 6 billion years ago, dark energy was stronger. 4 billion years ago, slightly weaker. Today, weaker still. The statistical significance is impossible to ignore. Multiple independent measurements all pointing to the same conclusion. Dark energy is not constant. It's changing, evolving, dying. Now, we need to be clear. This doesn't mean the Big Crunch is guaranteed. The data shows a trend, not a certainty. Dark energy could stabilize. It could weaken to some minimum level and remain there. The universe could still expand forever, just more slowly than we thought. But here's what keeps cosmologists awake at night. We don't know which scenario is correct. We don't understand what dark energy actually is. We don't know the rules it follows. We don't know if it can reverse entirely. We've mapped the universe across billions of light years and billions of years of history. And we've discovered that our fundamental model of reality might be incomplete. If dark energy is weakening, then everything changes. Everything we thought we understood about the cosmos suddenly becomes uncertain. Our theories about dark matter, about quantum mechanics, about the fundamental forces of nature, all of them were built on the assumption that dark energy is constant. If that assumption is wrong, we may need to rewrite significant portions of modern physics. Textbooks will need new chapters. Equations will need revision. The elegant mathematical framework we've constructed over decades may need to be dismantled and rebuilt from the ground up. Some theorists propose dark energy isn't a cosmological constant at all, but a field. Something dynamic, something that can change over time. They call it quintessence. Others suggest we're seeing evidence of modified gravity. That, Einstein's equations break down at cosmic scales, and the universe operates under different rules than we understand. Still others wonder if we're witnessing something even stranger, a sign that our universe exists within a larger multiverse, that dark energy's behavior is influenced by forces beyond our cosmic horizon. The truth is, we don't know, and that's terrifying and exhilarating. Because uncertainty means discovery. It means the next decade of cosmology won't be about confirming what we already believe, but about exploring genuinely unknown territory. DESI will continue mapping galaxies. Next-generation telescopes will push even deeper into space and time. New experiments will probe the nature of dark energy with unprecedented precision. We're living through a revolution in our understanding of the universe, not the kind that happens overnight, but the kind that reshapes everything we think we know about existence itself. Humanity has always looked up at the night sky and asked the deepest questions. Where did we come from? Why are we here? How will it all end? For most of history, those questions belonged to philosophy and religion. But in the past century, we've developed the tools to actually answer them. To map the universe, to measure its expansion, to calculate its fate. We thought we had the answer. The Big Freeze. A slow, inevitable decline into darkness. But now, DESI has shown us something profound. The universe is not static. It's not predictable. Even its death is uncertain. Whether we're headed for a freeze or a crunch, whether dark energy fades or persists, whether our understanding of physics needs a minor adjustment or a complete overhaul, these are questions that will define the next era of science. And perhaps that's the most important revelation of all. Not that we might have been wrong about the universe's end, but that we're still capable of being surprised. That after mapping millions of galaxies and measuring billions of years of cosmic history, the universe can still show us something we never expected. That reality is deeper, stranger, and more wondrous than even our best theories can capture. The universe will end. That much is certain. But how, and when, and why? Those questions remain beautifully, terrifyingly, thrillingly unanswered. And that's exactly how science should be.